Welcome back. In this section, we're going to be looking at the sum and difference identities for sine, for cosine, and for tangent. These identities have lots of uses. One of the most obvious uses, though, is that with these identities, we'd be able to find sine, cosine, and tangent of any multiple of 15 degrees, of pi over 12. So let's show you an example of that. I want to find what is cosine of pi over 12, and if I were thinking about that in terms of degrees, pi over 12 in terms of degrees is 15 degrees, and 15 degrees you could imagine as being 45 minus 30. So that means that if I'm looking for cosine of pi over 12, cosine of 15 degrees, I can do that as cosine of pi over 4, 45 degrees, minus pi over 6, 30 degrees. And now I'm just going to apply the cosine difference identity from the previous page. When we have cosine of one angle minus another, that's cosine of the first angle, cosine of the second, plus sine of the first angle, sine of the second. And then at this point now we're just really using our special triangles to evaluate. So root 2 over 2 for cosine of pi over 4, root 3 over 2 for cosine of pi over 6, root 2 over 2 for sine of pi over 4, and 1/2 for sine of pi over 6. And then just a little bit of cleaning up. And away we go. We've now got our exact value for cosine of pi over 12. It's root 6 plus root 2 all over 4. And so that was us using that angle difference identity. For the second example, I'm going to be using the angle sum identity. If we're looking at this 7 pi over 12, if you were to turn that into degrees, you would see that that would be 105 degrees, which you could imagine as being 60 plus 45. So that means if I wanted cosine of 7 pi over 12, I would say, well, cosine of 7 pi over 12 is the same thing as cosine of pi over 3 plus pi over 4. Pi over 3 plus pi over 4, that's 60 plus 45, that's 105 degrees. And now I have cosine of one angle plus another. I could just use my angle sum formula, which is cosine of the first angle, cosine of the second, minus sine of the first angle, sine of the second. And then the only thing left for me to do is just to evaluate and then clean things up. And again, special triangles are all I really need here. 1/2 for cosine of pi over 3, root 2 over 2 for cosine of pi over 4. I have root 3 over 2 for sine of pi over 3, and root 2 over 2 for sine of pi over 4. And then again, just a little bit of cleaning up. And I have my final result. So cosine of 7 pi over 12 is root 2 minus root 6, the whole thing all over 4. So like I said, these identities, we can use them both for angle sums and angle differences of cosines or sines or tangents. We'll see all 6 of them by the end of this video. But of course, as we see them, I'm just not going to give you just the formulas. We're going to actually derive them. So what we're going to do is we're going to start off assuming that we know one of these formulas to be true, and I'm going to show you how we can generate the other 5 formulas. So the one that we're going to assume that we know is the cosine difference formula. So we'll just take it for granted that we happen to know that cosine of alpha minus beta is cosine of alpha, cosine of beta, plus sine of alpha, sine of beta. So we'll just assume that that's something that we know already, and I'll show you how I can generate all the other identities from that. So if we wanted to come up with the formula for cosine of alpha plus beta, and I wanted to use the one identity that I already knew, then that means I'd have to rephrase alpha plus beta is a difference. And I can do that pretty easily because alpha plus beta is the same thing as alpha minus negative beta. So instead of having cosine of one angle plus another, I now have cosine of one angle minus another. And I can use the identity that I already know, which is it should be cosine of the first angle, cosine of the second, and then plus sine of the first angle, sine of the second. And then now, the only thing left for me to do is just use a couple of identities that I know. And one is the fact that sine is an even function. I know that cosine of negative beta is the same thing as cosine of beta, and that's because cosine is even. And I also know that sine is odd, that sine of negative beta is negative of sine of beta. So those are two little identities that I happen to know already. So using them here, the fact that cosine is even means cosine of alpha, cosine of negative beta is the same thing as cosine alpha, cosine positive beta. And since sine is odd, that negative can come out front, meaning I have now minus sine of alpha, sine of beta. And there we go. So if I knew the difference identity for cosine, I now can also get it out of it, generate from it the sum identity for cosine. Okay, so now we know the first two. We know cosine alpha minus beta and cosine of alpha plus beta. Next, what we're going to do is use those identities to generate the sine identities. And if you're wondering, how are we going to get sines out of this if we only know cosines? And the answer is the complementary angle theorem. So if we're flashing back to chapter 7, the complementary angle theorem said that when you have two angles that are complementary, two angles that add up to 90, and you've got two cofunctions like sine and cosine, then they would be equal. So if we had one angle theta and we had another angle 90 minus theta, then sine and cosine of those angles would be equal. So that's the idea here, is that we're going to rephrase our sine identity in terms of cosines, and then we'll be able to use the cosine identity that we already know. So that's kind of the idea here, that if we're looking for sine of alpha plus beta, I can turn it into cosines by saying, well, whatever this angle is, take the second angle to be 90 minus that. So now we've got two angles. I've got alpha plus beta is one of the angles. I've got 90 minus alpha plus beta, that's the other angle. These two angles are complementary. I have two cofunctions, so therefore these must be equal to each other. So I know that if I'm looking for sine of alpha plus beta, that's the same thing as cosine of 90 minus alpha plus beta. Okay, so I'm going to now do a little bit of extra work here to get this into where I want it to be. So one thing I'm going to do next is I'm going to carry that negative through the brackets. So I'll say actually what we have now is cosine of 90 minus alpha minus beta. Okay, and you might be wondering, why am I doing this? If I tried right now on the first line to use my cosine difference identity, I'd have cosine of 90, I'd have cosine of alpha plus beta, then I'd have sine of 90, and I'd have sine of alpha plus beta, which doesn't really help me because I don't know what sine of alpha plus beta is yet. So by doing this little bit of rephrasing, I'm going to get it into a form where I can actually evaluate. So the plan here is, instead of having 90 being one of the angles and alpha minus beta being the other, I'm going to have 90 minus alpha being one of the angles and beta being the other. So I'm just going to actually put a little set of brackets around here to make it really clear what I'm doing. So now, what have I got? Well, I have cosine of one angle minus another, and we already know our cosine identities, so I can go right ahead and use them and say that that should be cosine of the first angle, cosine of the second, plus sine of the first angle, sine of the second. And now as a little clever plot twist, you'll notice here I've got cosine of 90 minus alpha, and I know, courtesy of the complementary angle theorem, that that would be the same thing as sine of alpha. Because again, sine and cosine are cofunctions. Alpha and 90 minus alpha add up to 90, so you have two complementary angles, you have two cofunctions. That's how I know that sine of alpha and cosine of 90 minus alpha must be the same. Same thing over here, I've got 90 minus alpha again. Sine of 90 minus alpha should be the same thing as cosine of alpha. Again, courtesy of the complementary angle theorem. And now here we go. We've got sine of alpha plus beta is sine alpha cos beta plus cos alpha sine beta. We've got our identity for sine of alpha plus beta already nicely worked out for us. Okay, and now that we have sine of alpha plus beta, I guess the next natural move is to figure out sine of alpha minus beta. So let's do that using the formula for sine of alpha plus beta that we just figured out. Let's get sine of alpha minus beta, and same sort of an idea here. I'm going to take sine of alpha minus beta, which is what I want, and I'm going to rephrase it in terms of something which I already know. I know how sine formula for alpha plus beta works, so if I could rewrite this with a plus, that would be great, and that's not hard to do because alpha minus beta is the same thing as alpha plus negative beta. So I've rephrased this difference as a sum, and since I already have a formula for the sum, I can go right ahead and use it. And the formula for the sum of two angles for sine is sine of the first cosine of the second plus cosine of the first sine of the second one. And now, just like I did earlier, I'm going to use the even and odd properties for sine and cosine to help simplify this. Again, cosine is an even function, so it's going to just absorb that negative. And sine is an odd function, so that negative will come out in front. And there we go, we've got our formula for sine of alpha minus beta. All right, last two, we have the identities for tangent. I'm going to only do one of these, and I'll show you why after I do one of them. I'll do the very first one, tangent of alpha minus beta, and then once I've done that, I'll show you how the identity for tangent alpha plus beta could quickly be derived. So let's start off with this. If I'm looking for tangent of alpha minus beta, and I want to use things that I already know, well, I can use the fact that I know that tangent is sine divided by cosine, so that's really just sine of alpha minus beta over cosine of alpha minus beta. And I'm just going to now use both of my identities. Sine of alpha minus beta is sine alpha cosine beta minus cosine alpha sine of beta. And then the denominator, cosine of alpha minus beta, is cosine alpha cosine beta plus sine alpha sine beta. Okay, so this is lovely. It's a bunch of sines and cosines, but if you've taken a look at the formulas that we had above, you can see that they're all in terms of tangents, not sines and cosines. So of course, I know that sine divided by cosine gives me tangents. So if I'm thinking about this sine alpha cos beta minus cos alpha sine beta, how am I going to get some tangents out of there? One natural thought might be, well, if I divide it maybe by cosines, that might fix things. So that's what I'm actually going to do here. I'm going to take all of my four terms in the numerator and the denominator, and I'm going to divide all of them by cos alpha cos beta. So I'll have in the numerator sine alpha cos beta. I'll divide that by cos alpha cos beta. The second term, cos alpha sine beta, I'll divide that by cos alpha cos beta. And in the denominator, cos alpha cos beta, I'll divide that by cos alpha cos beta. And then the last term in the denominator, I've got sine alpha, sine beta, and we'll divide that by cos alpha, cos beta. Just realized I wrote cos beta twice here on that previous line. Let me just fix that. Okay, so I've now taken everybody, all the four terms, the two terms in the numerator, the two terms in the denominator, and I've divided them all by cos alpha, cos beta, and then a bunch of simplifying happens here because in the first term in the numerator, the cos betas cancel, and in the second term in the numerator, the cos alphas cancel, and in the denominator in the first term, the cosine alphas cancel and the cosine betas cancel. And so simplifying, what is this giving us? This is giving me just sine alpha cos alpha in the first term minus sine beta over cos beta. And then 1 and plus sine alpha sine beta over cos alpha cos beta. And now you can see your way to the end here because we can see that all these sine alphas and cos alphas are just going to turn into tangents, and sine betas over cos betas are also going to turn into tangents. So that first term, sine alpha over cos alpha, that is tangent of alpha. Sine beta over cos beta, that is tangent of beta. And then we have 1 plus tangent of alpha times tangent of beta. There we go. So that's establishing that identity that we had for tangent of alpha minus beta. If I wanted to do tangent of alpha plus beta, then instead of sine of alpha minus beta, it would be sine of alpha plus beta. And what that would do for me would just be to change the signs in the numerator and the denominator, change them from minuses and pluses to pluses and minuses. So I would be doing actually exactly the same steps if I decided to now justify why the formula for tangent of alpha minus beta works the way that, or alpha plus beta works the way that it does. But good enough. So I justified now all of our identities except for the very first one, that cosine of alpha minus beta. We just took that one for granted, but if we know one of them, we can now generate all of the other ones.